Welcome to Physics in Motion.
Hey, everyone.
Today, we're diving headfirst into something that's, well, everywhere and in everything. Forms of energy and energy conversion.
It really is fundamental.
Yeah, think about it like those huge explosions in a summer blockbuster movie.
Or even just, how your phone battery lasts through the day.
Exactly. It's all about energy, doing its thing and changing forms.
So our mission today is basically to unpack that. What are the main types of energy?
And how do they switch between those types? These transformations are happening constantly.
Right. We'll start with the absolute basics. What energy is.
Yeah.
That fundamental ability to cause change, to make things happen.
And then we'll get into the 7 main flavors it comes in.
Mechanical, chemical, electrical, electromagnetic, thermal, sound, and even nuclear energy.
And we promise this isn't going to be like studying for a test.
No, definitely not.
We're going to link these concepts to stuff you see all the time, maybe even like in that video game you were playing last night.
Or your favorite superhero flick. Hopefully you'll have some aha moments.
Yeah, it might just change how you look at things.
Okay, so let's kick things off maybe with the scene.
Yeah.
Picture a rock concert.
Oh yeah, perfect example. Loud music, flashing lights.
Totally. You've got the guitarist shredding on an electric guitar, colored lights sweeping over the stage.
And the crowd just feeding off that energy.
Exactly. That one scene, that snapshot, it shows us a bunch of different energy forms all working together.
Okay, let's break it down. The guitarist strumming the strings.
That's mechanical energy. Movement.
And where did they get the energy to even move their arms like that?
Probably from chemical energy, right? Stored in the food they ate.
Makes sense. Then you've got the stage lights. Big, bright.
Those are running on electrical energy, obviously.
Right.
Which they're turning into.
Light energy, so we can see. And thermal energy, too.
Definitely thermal. Ever stood near one of those big stage lamps? They get hot.
Oh, yeah. And don't forget the main event, the sound.
Right. Sound energy. Vibrations traveling from the amps through the air.
So that's
Yeah.
mechanical, chemical, electrical, light, thermal, sound.
Did we miss any major ones from the concert scene?
Well, the 7th one, nuclear energy, isn't usually rocking out on stage.
Good point.
But it's a fundamental form we should touch on. It towers stars, nuclear reactors, important stuff.
Gotcha. Okay, so let's maybe define these 7 forms a bit more clearly, starting with mechanical.
Sure. Mechanical energy is basically the energy something has because it's moving or because it could move.
Yeah.
Its position gives it potential.
Like the drummer you mentioned.
Yeah, think about the drummer. When their sticks are hitting the drums, moving fast.
Kinetic mechanical energy.
Motion.
Exactly.
But what about when they lift a stick up right before they put it down? It's paused for a split second.
Potential energy. Because gravity is about to pull it down. It could move.
You got it. Potential to move.
Okay. Next up, chemical energy.
Right. This is the energy locked away inside the bonds between atoms and molecules. Think microscopic storage.
Like in batteries. For, say, a wireless guitar pack. Perfect example. Inside that battery, chemical reactions are happening. Bonds break. New bonds form.
And that releases the stored chemical energy.
Yep, releasing it as electrical energy to power the transmitter.
Which brings us neatly to electrical energy, number 3.
This one's all about moving electrons. Tiny charged particles flowing, usually through wires. That flow is electric current.
And that current can power things, like the whole sound system, the lights.
Absolutely. Amplifiers, microphones, mixing desks, all running on that flow of electrons, that electrical energy.
Okay, form number 4, electromagnetic energy. This one sounds a bit more complex.
It travels in waves, yeah. Waves that have both electric and magnetic parts. Light is the most obvious example.
So the light from the stage lights is electromagnetic energy.
Yep. But that spectrum is huge. Radio waves carrying signals, microwaves.
Like in a microwave oven.
Exactly. And even higher energy stuff like X-rays and gamma rays, all part of the same family.
Wow, okay. Number 5, thermal energy. Heat, right?
Essentially, yeah.
Yeah.
It's the internal energy of stuff due to its atoms and molecules jiggling around. The faster they move, the more thermal energy.
So more jiggling equals hotter.
Basically. And also, if you have more stuff, more atoms, you have more total thermal energy, even at the same temperature.
Like someone dancing hard in the crowd at that concert?
Good example. They're using chemical energy, their muscles work, things heat up internally. Their thermal energy increases. They might even start sweating to cool down.
Oh, okay. Number 6, Sound energy.
Sound. We talked about this at the concert. It's actually a type of mechanical energy.
Oh, right, because it involves movement.
Vibrations.
Exactly. Vibrations traveling through something, air, water, even solids, like waves,
So the singer's vocal cords vibrate.
causing air molecules to vibrate, creating sound waves that reach your ears.
And sound needs something to travel through, right? Can't travel in space.
Correct. No air, no sound. So those epic spaceship battle sounds in movies.
Pure Hollywood magic.
Got it.
Pure Hollywood, yeah.
All right, last one. Nuclear energy, the big one.
Yeah, this is the energy stored right inside the nucleus, the very center of an atom, held together by incredibly strong forces.
And you get it out by splitting atoms.
That's one way, called nuclear fission. It's what nuclear power plants do. Or through radioactive decay, where unstable atoms release energy naturally over time.
Okay, so those are our 7 forms. Mechanical, chemical, electrical, electromagnetic, thermal, sound, nuclear.
Nailed it.
But the really cool part, I think, is how they change into each other.
Ah, yes. Energy conversion. That's where the action is. Energy rarely just sits there in one form.
It's always transforming. And this is crucial. It's not like the energy gets used up or disappears when it converts.
Yeah, absolutely. Key point. It just changes its outfit, so to speak. That's the law of conservation of energy.
Energy cannot be created or destroyed, only converted from one form to another.
The total amount always stays the same in a closed system.
Okay, let's think about an example. Maybe something less concert-y, like movie night at home. Making popcorn.
Perfect. That whole scenario relies heavily on electrical energy from the wall socket, right?
Yeah, but where did that often come from?
Well, a lot of the time, it might start way back at a power plant burning fossil fuels,
So that's chemical energy stored in the fuel,
getting converted to thermal energy when it burns.
which is then used somehow to generate electrical energy. Wow, a whole chain.
It's often a multi-step process, yeah.
And then the popcorn machine, or the microwave itself, you plug it in.
Right. So electrical energy goes in if it's a microwave.
It makes microwaves, which are electromagnetic energy.
You got it.
Yeah.
Electrical to electromagnetic. Those waves then zap the water inside the kernels.
Making the water molecules vibrate like crazy, increasing their thermal energy.
Exactly. They get hot. Really hot.
Until POP.
POP, which is mechanical energy, right?
Yeah.
The kernel explodes outwards, moves around.
And you hear the pop. That's sound energy.
Look at that. Electrical to electromagnetic to thermal to mechanical and sound energy. All from making popcorn.
Pretty cool.
It really is.
Now, you mentioned mechanical energy earlier, kinetic and potential. That seems like a really common conversion pair.
Oh, absolutely. It's happening all around us. Remember, kinetic is energy of motion.
And potential is stored energy, usually due to position or maybe shape, like a stretched rubber band.
Right. Think about a character in a video game, maybe standing on a high platform.
Okay, like Mario on top of a block.
Perfect. Up there, not moving yet. They have stored potential energy because of gravity. Height equals potential.
Then they jump off.
And as they fall, that potential energy converts into kinetic energy. They speed up, right?
Yeah, fastest just before they land. So maximum kinetic, minimum potential at the bottom.
Pretty much, yeah. Most of that stored potential energy has become energy of motion.
And to get back up there, to regain that potential energy.
They got to jump or climb, right? They use kinetic energy muscle movement to work against gravity.
And store that energy back up as potential energy at the height. It's a cycle.
Exactly. You see this cycle constantly. Swings in a playground.
A skateboarder in a half pipe, max potential at the top edges.
Max kinetic zooming through the bottom.
Yeah.
Trampolines, roller coasters.
Even just bouncing a ball.
Yeah.
You can totally picture this in games with good physics engines too, can't you?
Yeah.
When characters jump, fall, use grappling hooks.
Definitely. That back and forth between potential and kinetic energy is everywhere in simulations and the real world.
And these conversions aren't just in games or big machines. Our everyday gadgets do it too. My phone charging right now
Electrical energy for the wall outlet.
is being converted into chemical energy stored in the battery, ready for later.
Or think about a car starting up and driving off.
Okay, chemical energy in the gasoline.
Gets converted to thermal energy when it ignites in the engine.
And that heat expands gases, pushing pistons, making things move.
Yeah.
Thermal to mechanical energy.
Right, to turn the wheels and get you going.
And what about, like, in a fantasy game? A wizard casts a lightning spell.
Ooh, good one. That could be seen as maybe some internal magical energy converting to electrical energy.
Which then zaps out as bright light electromagnetic energy and probably makes a loud crackle, sound energy, and generates heat where it hits, thermal energy.
Exactly. Multiple conversions happening to create that effect.
Okay, wow. So let's maybe try and wrap this up, pull it together.
Sounds good. So we've seen energy isn't just one thing. It comes in these 7 main forms.
Mechanical, chemical, electrical, electromagnetic, thermal, sound, and nuclear. From a bouncing ball to Wi-Fi signals.
And the really big idea, the key takeaway perhaps,
Is that these forms don't stay put. They're constantly changing, converting.
through energy conversion, yeah. And always, always following that fundamental rule, the law of conservation of energy.
No energy lost, no energy created, just transformed.
So why does this matter? What's the big picture?
Well, understanding these conversions helps us make sense of pretty much everything. How a power plant works, how our bodies use food, how technology functions.
From the simplest things to the most complex.
Yeah, here's a challenge for you listening. Next time you're watching a movie with crazy special effects, just pause and think.
What energy conversions might be happening behind the scenes to make that explosion look real, or that laser beam fire?
Or if you're deep into a video game with realistic physics, watch how things move. Spot the kinetic and potential energy swapping places.
It adds a whole new layer, doesn't it?
Totally. Which leads to maybe a final thought for you to ponder.
Ooh, I like a pondering question.
Can you look around right now, wherever you are, and identify maybe 3 different energy conversions happening right now?
Give it a shot. You might be surprised how many you find.
It's a great way to see this stuff in action.
Definitely.
And with that, we should probably wrap up. But before we go, a very special shout out
Nice.
to the Geeky Gamer Science teacher for creating this awesome learning experience.